We've now encountered a few gas laws dealing with pressure, volume, and temperature, but the thing they all had in common was that the amount of gas we were dealing with needed to be held constant. Now we come to the gas law, the ideal gas law, that deals with all four of these variables. All the previous gas laws and the amount of moles can be combined into one new gas equation called the ideal gas law. It was created by Emile Clapeyron in 1834. One of the most important parts of the kinetic molecular theory that you already learned about is how it explains the ideal gas law. In ideal gas, we assume that the volume of each particle is insignificant when compared to the volume of the container. You could think of them as little dot particles moving around. All of the collisions are elastic, meaning no energy is lost when a particle bumps up against a wall or another particle. And there are no forces of attraction that exist between the particles or between the particle and the container. So that's not true for real gases. We know that the electrons of a gas particle can, for a few moments in time, be on one side compared to the other side, and you get a little instantaneous dipole. So for our ideal gases, we assume that doesn't happen, and that even if they get very close together under very high pressure or very low temperature, we assume that they're not sticking together to start forming a liquid. Here is the ideal gas law. PV equals nRT. We've seen pressure, volume, number of moles, and temperature before. This R is a gas constant. So R is just a number. That number depends on what your units are. So when you're dealing with liters, atmospheres, and Kelvin, your R is going to be this very small number, 0.08206. If you look up the ideal gas law constant online, you'll see a lot of different numbers, but those are different numbers for dealing with different units. So here we have a problem for the ideal gas law. If a scientist has a sample of ammonia in a volume of 2.15 liters at standard temperature and pressure, that's 0 degrees Celsius and 1 atmosphere, how many moles of methane are in that sample? So we finally have an equation that can tell us how many particles we have if we know all of this other information. The first thing I'm going to do is write down what we know. They tell us the pressure, that's 1 atmosphere. They tell us the volume, 2.15 liter. We don't know the number of moles, that's what we're trying to find. R is just a constant. That's in liters, atmosphere, per mole Kelvin. And the temperature, 0 degrees C plus 273.15, because we can only do gas law equations in Kelvin. So 273.15 Kelvin. Next we use the ideal gas law. PV equals nRT. We know pressure, 1 atm. We know volume. We know that's equal to N, which is what we're looking for. R liters atmosphere per mole Kelvin, and our temperature, so you can see Kelvin here will cancel out. What we have is a number here, and that is equal to our number of moles multiplied by a different number. So I'm just going to simplify now. This side of the equation, 2.15 liters atmosphere is equal to N times 22.41, and what we have left here, liters, atmospheres per mole. The last thing to do is divide each side by 22.41 liters atmospheres per mole. And we're done.